Welcome. This is George. He's doing his master in data science, and today he will explain the risk assessment of an investment portfolio considering rare events.
Yes, and for this, I'll take you with me to Riga. Come on. Started with the first joint evening dinner in the Lido. The next day we had a nice breakfast, and then we made our way to the RTU University to have a nice tour through the building. Gut. We arrived at the SEB Bank and heard a nice presentation about innovation. On the next day, we held our presentation that we prepared in cooperation with the students of Riga. So that's me doing my presentation, but first let's recall what my topic was actually about. So the title was Risk Assessment of an Investment Portfolio Considering Rare Events. But before we begin, the guy on the right is me and the guy on the left is Daniel, my counterpart from Riga. The main goal of my presentation was to show what can happen during rare events and how strongly they can impact a portfolio. We also explored a commonly used method to model joint behavior, namely the copula functions. Let's start with a prominent example. The global financial crisis from 2007 to 2009. We compared two tech stocks, Apple and Microsoft, before, during, and after that period. Even at first glance, you can see that both stocks experienced crashes at similar times during the crisis, and the correlation within the crisis window is noticeably higher than over the full sample, indicating stronger independence during extreme market conditions. This suggests stronger dependence during extreme situations, a phenomenon known as tail dependence. But how do we actually measure tail dependence or other risk measures between assets in a portfolio? That's where the copula functions come in. Their goal is to help us better understand the joint distribution of the transformed margins, giving us a joint model that we can use to simulate portfolio values. So how would we proceed? The idea is to first estimate the marginal distributions of each asset individually. Next, we transform the data into pseudo-observations, values between 0 and 1, using these marginal CDFs. Plotting these against each other already gives us a first impression of the dependent structure. To make this more concrete, let's take Nvidia and Tesla as an example. The next step is probably the most challenging one, selecting an appropriate copula. A good starting point is to visually inspect the pseudo-observation plot, look for patterns in the dependent structure, and analyze the tail behavior. Other useful tools are goodness of fit tests or information criteria like AIC or BIC. From there, we can choose a copula family, for example a T-copula for stronger tail dependence, or a Gaussian copula if joint extremes are less pronounced. And estimate the parameters, for instance using maximum likelihood. In our case, since we observed evidence of tail dependence, a T-copula could be a reasonable choice, at least for this particular example. However, it's important to note that choosing two stocks from the same sector naturally increases the chance of strong dependence. To illustrate how dependent structures can look different, let's briefly look at another pair of stocks from different industries. Here, the dependent structure appears much weaker, especially in extreme situations. This highlights why the choice of assets matters and why copulas are useful. They allow us to model very different types of relationships within a portfolio. Once we have selected and fitted a copula, we can use it to simulate returns, estimate tail dependence, and calculate further risk measures. Alright, that's it for the theoretical part. Enjoy the rest of the video. After we held our presentations, we visited the LMT and had a nice workshop there. After that, we had a nice guided tour through Riga. A beautiful view of Riga in the Swedbank, where we heard a nice presentation of different types of risk models. And then we had our last evening together at a local restaurant.